Hello students, Mr. Courtney here. In this video, we're going to be covering bonding. We're going to talk about ionic bonds, covalent bonds, metallic bonds, and also we're going to look at the Lewis dot structures for elements, compounds, whether they're ionic, covalent molecules, and so on. So let's talk about the type of bonds. Now the type of bond depends on how strongly the atoms that are bonded attracts the electrons. That is, how strongly they pull on the electrons. And so that's how strongly they pull on electrons. We're looking at the pull on electrons. When we talk about the pull on electrons, what are we talking about? Remember, we're talking about electronegativity. Okay, so we're talking about electronegativity. So we look at the difference in electronegativity. That is what is going to determine if it's ionic bonds, covalent bonds, and then covalent bonds could either be polar or non-polar. And it all depends on the difference in electronegativity. If that difference is between 0 and 0.4, it is going to be non-polar. When we talk about non-polar, we talk about equal sharing of electrons. When we talk about polar covalent, where it is greater than 0.4 but less than 1.67, or sorry, rather greater than or equal to 0.4 but less than 1.67, there's going to be unequal sharing of electrons. And I should write that, unequal sharing of electrons. In ionic compounds, there's a difference. If it's greater than or equal to 1.67 up to 4, then it's going to be ionic. So the bond is going to be ionic bond. So now we're going to talk in detail about the types of bond. We start with ionic bonds. In an ionic bond, it results from the attraction between a positive ion and a negative ion. The difference in electronegativity is greater than or equal to 1.67. So that means if we take the electronegativity of the two elements or the elements in the bond and subtract them, find the difference, it's going to be greater than or equal to 1.67. It's going to be formed between a metal and a non-metal. So if we have a great electronegativity difference, this is going to be close to the most electronegative element, which is close to fluorine. This is going to be far from fluorine. Okay, so in this case now we have a transfer of electrons, or a loss and gain. So the atom's going to lose or gain electrons. For there to be an attraction between ions, we have to form these ions, and the way these ions are formed is that our metals will lose an electron and our non-metals will gain an electron. So in this case here, sodium loses an electron and chlorine gains that electron. So sodium now forms an ion and chlorine now forms the chloride ion, and they form a bond between these two elements. Okay, so if we look at the properties now of these ionic compounds, they're going to have a high melting and boiling point, meaning that you require lots of energy to break the bonds between these compounds. So the bonds are going to be strong. So we can say they have strong bonds. Volatility, ability to turn into a gas. And that's one way of kind of putting it. How well they can turn into a gas. And if they can turn into gas, then we can smell. They can be smelt. You can smell them when you think of odor. So if they have low volatility, that means they have low or no odor. They conduct electricity in aqueous or molten state. Most of them are able to dissolve in water, not all. And they're going to have strong, rigid crystalline structure. So the bonds, they're going to be rigid. The attraction between these ions are going to be strong. So that makes the bond strong. Rigid. They have very little movement, so they do not readily move from in large positions. They move about a small position. They're going to be crystalline in structure. That means they're able to form crystals. And let's go back here. When we talk about aqueous, we mean in dissolved in water. If it's dissolved in water, then it's going to be called aqueous. A covalent bond results from the stability of full outer energy levels. So that means these atoms want the outer energy levels to be full. The difference in electronegativity is less than 1.67 as we saw before. And we could have polar covalent or non-polar covalent. Now it's a bond between two non-metals. So that means these two are relatively close to each other. They're closer to fluorine. The difference in electronegativity is small, so that means we have two nonmetals. Now remember, nonmetals tend to want to gain electron. So if we have two nonmetals and they both want to gain electrons, the best compromise is to share electrons instead. So they share electrons to fill their outer energy level, as we see here in a bond formed between carbon and hydrogen. Hydrogen needs 2 electrons to be stable. Carbon needs 8 electrons to be stable in its valence energy level. Here, the blue ones represents those donated by carbon. The red ones, those donated by hydrogen. So, 1, 2. They share electrons here. Hydrogen has 2 electrons, is good. Hydrogen has 2 here again. Hydrogen has 2. Hydrogen has 2. So the 4 hydrogens have 2 electrons. Now let's look at a carbon. These 2 are shared with carbon also. These 2, these 2, these 2. So that gives it a total of 8. So by sharing the electrons, they both end up with a stable or a filled outer energy level. Now these compounds are going to have low melting and boiling point. So that tells us the bonds are weaker than that of carbon. Well, most of them. High volatility. High volatility, or they have a great odor. So you can readily smell these compounds. They do not conduct electricity whether in molten or aqueous form. And most of them do not dissolve in water. Most. And I give an example here. Sugar is a covalent compound and it's able to dissolve in water. And they may have a soft crystalline structure. That means they can form crystals, but the crystal will not be as strong or rigid as those formed by ionic compounds. So let's talk about a new type of bond. I know you've looked at ionic bonding, you've looked at covalent bonding before. Now let's look at metallic bonding. This may be new to you. It's a bond formed between metals. And maybe I should have specified here, metals are atoms of the same metal. So it's not like between gold and silver. No. They don't form bonds between gold and silver. Instead, it's between metals, atoms of the same metal. So between gold atoms, as we see in this diagram here, are silver atoms, if this represented silver. We do not need to know anything about electronegativity. So electronegativity has nothing to do with that. The atoms can achieve a more stable configuration by sharing the electrons in their valence energy shell with other atoms. So these electrons here are the electrons in the valence energy shell. And as you can see, they are shared with other atoms. And that's indicated by the movement. The dashes, the small dashes here represent the different positions they could be at. And the dots represent the point where they're at that point in time. So, and that's what we talked about, that sea of electrons, meaning that we have electrons or mobile electrons. These electrons are in constant motion as they move from one atom to another. So they don't stay still. Instead, they're shared from one atom to another. That's how they achieve their stability. And we talk about that sea of electrons. Compounds that have metallic bonds, they have a high luster. That means they have a shine, great shine about them. Not sure if you can see these properly here. They're also malleable and ductile. If it's malleable, that means you can be made into it can be flattened. So if it's malleable, it can be flattened. Alright, so it can be flattened. Ductile. Can be made into wires. And when we talk about flattened, maybe I could say it can be flattened or made into, think of sheets, thin sheets. As we see here, example, we have copper. Copper is made into some copper foil or copper sheets here, and that same copper is also made into copper wire, which is turned into a spring or a coil. They do not dissolve in water, so they're, and I didn't mention this before, when we talk about the ability to dissolve in water, we talk about solubility. If it can dissolve in water, it's soluble. If it does not dissolve in water, it's insoluble. Okay, they're going to have high melting points. All right, if they have high melting points, that means they're also going to have high boiling points. Right, so let's review Lewis structure of atoms. All right, and this diagram here basically sums it up. Based on the number of electrons, valence electrons, we have the examples and we have the Lewis dot structures. If they have one valence electron, like hydrogen, we have 1 dot, or all the elements in group 1, you have 1 dot. 2, like helium and group 2, or the alkali earth metals. All right, alkaline earth metals, they have 2 dots. Group 3, they have 3 dots. Group 4, 4 dots, because they have 4 valence electrons. So remember that the number of valence electrons is indicated here. So for the next set of stuff we're going to do, you're going to need your periodic table. So if you don't have it out, pause the video, go ahead and get your periodic table. And remember the representative group elements, group 1, group 2, 3, 4, or we say 4A, 14. So look for those with the A's next to them on the periodic table. And these are the ones that determines the number of valence electrons they have. Okay, so let's look at an electron transfer diagram. And because we use the word transfer diagram here, we said we're looking at the reaction between a metal and a non-metal. What type of bonds are we looking at? So, right, we're looking at ionic bond. So the formation of ionic bond. And the first one we're going to look at is the example between sodium and chlorine. So we need to find sodium on the periodic table. Remember, sodium is in group 1, so you're going to have 1 valence electron. So that's 1 dot. Chlorine is in group 7, so he's going to have 7 dots. I'm not going to put them in the correct position for now. I'm just going to do it so it makes it easier for me to get this done. So these are the 7 dots. Now, we talked about transfer of electrons. So the metals will lose, and the non-metals will gain electrons. So sodium is going to lose that 1 electron to chlorine. In the end, because sodium loses that electron, we represent sodium without that valence electron. We put it in parentheses and we write the charge because it's now the sodium ion. Chlorine gained 1 electron, so it now has 8 electrons. It is also an ion. So to represent an ion, we put it in parentheses and it has a negative charge. Sodium has 1 less electron than proton, hence the positive charge. Chlorine has 1 more electron than proton, hence the negative charge. Okay, let's look at calcium and chlorine. And I think you may have bromine in your notes, but you can change the bromine to chlorine. So calcium. Okay, so let's write calcium has 2 valence electrons, and I'll represent this in a different color. And then chlorine, we just did that. Chlorine has 7 valence electrons. So I've put my 7 valence electrons here. Now calcium needs to lose 2 electrons. So it loses 1, but it still needs to lose 1 more. So in the end, what is going to give us, we get the chlorine now. with the 8 electrons around it, because it gained those electrons, 1, 2, 3, 4, 5, 6, that's it, 7, plus the 1 it gained from calcium. And that's in parentheses, has a negative charge, -1. One more electron than proton. Now, but calcium still needs to lose one more. So what does that tell us? That means we need another chlorine to take part in this reaction, because we need 2 chlorine atoms. So, because calcium has 2 electrons to give. So the next electron is going to be donated here. So that gives us 2 of these in the end. Plus, we're going to have our calcium forms the ion of +2. So that is our electron transfer diagram, because it shows the transfer of electrons. Now notice, in the end, the metal ion does not have any electrons around them. Sodium lost its 1 valence electron, calcium lost its 2 valence electrons. All ions are in a square bracket with the charge on the outside. The non-metal has 8 valence electrons around it. So if we had used bromine here, bromine would be the same way with 8 valence electrons. If we use oxygen, 8 valence electrons around it. So now let's look at Lewis dot diagrams for covalent compounds. So we're going to show the sharing of electrons in covalent compounds. The electrons can be represented in 2 ways. Either by a dash, or by dots, which represent lone pairs. So the dash represents shared electrons. The dots represent lone pair of electrons. Now, each atom donates 1 electron to the bond. So how many electrons do we have in a covalent bond? That means we're going to have 2 electrons. So each dash represents 2 electrons. So when we check, this dash represents 2 electrons. Hydrogen has 2 electrons here. Hydrogen has 2 here because it's sharing. Hydrogen also has 2. So these 3 hydrogens have their valence shell filled because they're sharing 2 electrons with nitrogen. Now look at nitrogen. 2, 4, 6, 8. Now it also has 8 valence electrons. So that's what we look at. Okay, so let's look at how do we determine the number of bonds in a compound, in a covalent compound. We need to know the number of needed electrons. So that's 8. That is, how many electrons does it need to be stable? How many electrons in its valence shell does it need to be stable? All atoms need 8 except hydrogen, which needs 2. The number of available electrons, we depend on valence electrons. So we're going to look at 4 examples here. In carbon monoxide. Okay, we have 8 and 8, 16. Carbon has 4 valence electrons. Oxygen has 6. 6 plus 4 is 10. N minus A divided by 2. That gives us 3. Alright? Nitrogen. We have 2 nitrogen atoms, each requiring 8, so that's needed 16. Each nitrogen has 5 valence electrons, so that's available 10. And we're going to divide by 2. So 16 minus 10 again is 6 divided by 2. That gives us our 3 bonds, which is the same as what we did back here. Oxygen. Again, 2 oxygen atoms, each requiring 8. So we need 16. Each oxygen has 6 valence electrons, so 6 2s are 12. And we're going to divide by 2. So that is 4 divided by 2. And that gives us 2 bonds. In bromine, 2 bromine atoms, each requiring 8. So that's 16. Minus, each bromine has 7. 7 2s are 14. Divide by 2. So that is 2 divided by 2. So that is equal to 1 bond. So that's how we determine the number of bonds. And we're going to need that later on when we do drawing the structures. Okay, so you can take your time and read through the rules. First thing we need to do, and I'm just going to go through rules 1 and 2 with you, or rules 1, 2, and 3. We need to calculate the number of bonds first using the formula we just used, and just like we just did. We need to place the least electronegative element as a central atom. That is the one that is furthest away from fluorine. Fluorine is the most electronegative, so the further away you go from fluorine is the least electronegative it will be. Now, we can have any element except hydrogen. Okay, so you need to make note of that. It can be any elements except hydrogen. Hydrogen could never be the central atom. And then we connect the atoms with the number of bonds we determined from step 1. And we're going to go through this as we look at the following examples. So we looked at the number of bonds here already. Okay, so I'm going to do it in a slightly different way to how we did it. So we did N, A. We're going to also look at how many would be shared, and we're going to look at the number of bonds. N is how many are needed. We said we needed 16. Available was 10. So we do 16 minus 10. That is 6 electrons will be shared. How many bonds will be? 6 divided by 2. So we get 3 bonds. Okay? So it's 2 electrons per bond. So it doesn't matter which one is in the middle because it's 2 elements. So either we do carbon, oxygen, and we just determined we need 3 bonds. 1, 2, 3 bonds between these two. No, we looked at our electrons. Count your electrons now. 2, 4, 6. Our carbon still needs 2 more electrons. So we add our lone pair here. Sorry. Oxygen still needs 2 more, so we add another lone pair. So that gives each of these 8. Now count your electrons. We use 2 here, 4, 6, 8, 10. And we had 10 available. So that's our structure for carbon monoxide. In nitrogen, we needed 16. We had 10 electrons available. That means we had 6 electrons shared. And to get our bonds, we divide the shared electrons. So we take 6 divided by 2. That gives us our 3. Again, it doesn't matter which one goes in the middle. Nitrogen, nitrogen. They're going to be 3 bonds. 1, 2, 3. And each nitrogen would have 6, 2, 4, 6. So we need 2 more. So we put a lone pair or 2 electrons on each. Remember, 2 electrons make a lone pair. We have, if you count, 2, 4, 6, 8, 10. And we also had 10 available electrons. So that takes care of that. All right, so for oxygen, we said we needed 16. We had 12 available, and I'm just going back based on what we did before. So the shared will be 4, 16 minus 12, and the bonds will be 2. So it's a different way of calculating bonds. Same thing we did before, just doing it a different way. Now oxygen, we know we needed 2 bonds, so we have to put 2 bonds between here. Each oxygen has 4 electrons, but it needs 8. So that means we need to add 4 more electrons or 2 more lone pairs. So add 2 lone pairs here. 2 lone pairs here. So that gives us 2, 4, 6, 8. 2, 4, 6, 8 for each oxygen, or in total 2, 4, 6, 8, 10, 12. We had 12 available, so that's taken care of. Bromine. Bromine needed 16. We had 14 available, 7 from each bromine atom. So that means we had 2 shared. Bonds will be equal to 1. So bromine and bromine. Put one bond between them, and that's it. That's 2 electrons for each bromine, so they need 6 more, or 3 lone pairs. So add 3 lone pairs around each bromine atom. Ooh, that's a big one. There you go. And if you count your electrons, 2, 4, 6, 8. 2, 4, 6, 8 around each one, so we're good. 2, 4, 6, 8, 10, 12, 14. We had 14 available. So on these now, so we start by calculating how many is needed, available, we do shared, and we calculate our bond. So for nitrogen, for needed, we know hydrogen needs, hydrogen needs 2, so that's 2 times 2, plus oxygen, which needs 8, so that gives us 12. How many are available? 2 hydrogen atoms with 1 valence electron each, plus the 6 from oxygen, that gives us 8. So in terms of shared, we're going to have 12 minus 8, which is 4. Our bonds will be shared divided by 2, that is 2. Which one is the least electronegative? Remember, hydrogen could never go into the middle. So oxygen goes into the middle. Hydrogen, hydrogen. These are our 2 bonds. Hydrogen has 2 electrons around each one, so they're good. Oxygen only has 4. So they need 4 more electrons, or 2 more lone pairs. And if we count our electrons, 2, 4, 6, 8, and we also had 8 available. So that takes care of that. Okay, so let's look at these ones now. And these ones are a bit different. These are polyatomic. And poly means many. Atomic comes from the word atom. So that means many atoms. If it's a polyatomic ion, it's many atoms bonded with a charge. So they're covalent compounds. They're bonded, but they have a charge. So we have many of these joined together. Many atoms joined together resulting in a charge. So we're going to do the same thing. It doesn't matter. We start with how much is needed. The number needed. Sulfur would need what? 8. Plus 4 oxygen. Each would need 8. 4, 8. Sorry. So we get through that. Okay, so that gives us 8 fours, 4 is 32, and 8 is 40. So we have 40 needed electrons. Available, we have 6 from sulfur, plus 4 atoms of oxygen, each with 6. But we have -2 charge. That means we have an extra 2 electrons. And if you look back on the step, it tells you if you have a negative charge, then you need to add that number of electrons. So that would give us a total of 4 6s are 24, and 6 is 30, plus 2 is 32. So that means our shared will be 8, and our bonds will be 4. So which is more least electronegative? Sulfur. Sulfur goes into the middle. We put 4 oxygen atoms around it. We connect them with bonds. 2, 3, 4. We check our central atom. It has 2, 4, 6, 8 around it, so it's good. Now oxygen, each oxygen has 2, so that means we need to add 3 sets of lone pairs to each, or 6 electrons to each. Okay, and that is what we do. So do that, and when you finish that, check the total number of electrons you've used, and it will add up to the number available. If it doesn't add up, that means you did something wrong somewhere. So if we check together, that is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. So there you have it. Okay, and the last time we look at the hydronium ion, H3O+, we look again. We start with how many is needed. 3 hydrogen atoms needing 2, plus oxygen needing 8, not 6. So that gives us a total of 14. How many electrons are available? 3 hydrogen atoms with 1 valence electron each, plus the 6 electrons. Now they have from oxygen. Now with the positive charge, that means we have one more proton than electron, or one less electron. That means we need to subtract. So that's 6 plus 3 is 9, minus 1 is 8. Shared electrons will be 6. Bonds will be 3. So least electronegative goes in the middle, but in this case it cannot be hydrogen, so we have oxygen. We put our hydrogens around it. Then we connect them with the number of bonds. We had 3 bonds. 1, 2, 3. Each hydrogen atom has its 2 electrons. 2, 2. Oxygen only has 2, 4, 6. So that means we need to add 2 more electrons, or a lone pair. 1, 2. And if we check, 2, 2, 2, so the hydrogens are stable. Oxygen is stable. 2, 4, 6, 8. Because remember, each dash represents 2 electrons. And if we check our available electrons, we had 8, and we also count how many electrons we use. 2, 4, 6, 8. Okay, so that takes us to the end of this. And alright, take your time, go over it as many times as you like. So you have this available as a tool. Until the next time, I'm out. Blessings.